Thank you very much. Any other questions? Okay, we'll move on. It's my honor to introduce Dr. Aaron Clauset. Aaron is an associate professor at the University of Colorado at Boulder, where he is a member of the computer science department. He's also a faculty member at the Santa Fe Institute, a well-known think tank in the West. Aaron has a BS in physics from Haverford and his PhD in computer science from the University of New Mexico. He is also widely published and will be describing some of his work today. His talk is entitled Predicting the Unpredictable in Violent Political Conflict. Thank you for your participation, Aaron. He's over here. Do you want to wear the mic or speak from here?
I'll wear the mic.
Okay. I think it's that gadget right there. He can help you to set it up.
Okay, so this is a talk about violent political conflict. In violent political conflict, we're typically thinking about large events. And that's because these things have disproportionate impact on everything. So we don't care so much about, say, terrorist attacks that kill one person. We care about the ones that kill 100 people or 1,000 people. So we also care about international wars, large civil wars, things like that. These are all violent political conflicts. Events in violent political conflicts, but they are rare, and that makes it very problematic for making predictions. So for instance, if we think about the last 100 years of international war, there have only been 7 that killed more than 100,000 people, which I think we would all agree would be quite severe. And in large terrorist attacks, there have only been 37 events in the past 40 years that killed more than 100 people. So if you're going to do analytics on such a small data set, it's going to be a bit tricky because there's just not a lot of data to learn from. So because these events have disproportionate impact, we can ask a question of, well, can we predict them at all, especially with algorithms? So can we use data as a way of giving us some hint about whether or not something is going to come down the pipe? I think the answer is no. Maybe not a very inspiring answer, but it's important to note that I've added this caveat here with algorithms. Because really it depends. So if we want to predict things in the specific, if we want to say who is going to do it, what is going to happen, where it's going to happen, why, how, and when, then I think the answer is almost certainly no, we can't do this with algorithms. And the reason is because the events are rare. There is not enough data to build a good predictive model off of these things. There are too many relevant variables that we might want to try to understand that are important to whether these things happen. There's too much historical contingency, too much human agency, and too much incomplete information. So as a result, we try to build some massive machine learning model by sucking in a huge amount of data, say from the various kinds of data feeds that the national intelligence community has. There simply won't be enough signal there in order to predict these small number of events from such a massive amount of data. In other words, the problem is massively under-constrained. As a result, what these methods will tend to do is they'll overfit the past. They'll say, I expect to see an event exactly like the one I saw before, because it's the only event that I have to learn from. I can't see the correlations in this space because the space is too high dimensional. And as a result of overfitting the past, we will underfit the future. We'll miss the things that are coming down the line because they won't be exactly like the past. So what this tells us is that you can't really replace human expertise and evidence trails if you care about predicting things in the specific, if you care about the who, what, where, why, when, and how. But all hope is not lost. If you want to predict things in aggregate, then you can use data in order to make some kind of statistical forecasts or risk estimates. So these things are going to be inherently probabilistic. They're going to be inherently about the population as opposed to the individuals. And they are possible because there are these robust statistical patterns that exist in these data sets. And these things do correlate to some degree with the kinds of events that we care about, but only in aggregate. It's these kinds of statistical patterns that allow us to make these probabilistic estimates over the populations, not over the individuals. So as David was saying, it's kind of difficult to predict how Jake is going to vote. It's kind of difficult to predict how an individual terrorist is going to carry out an attack, if they are going to carry out an attack. But if you want to make a prediction about a population of people, then the central limit theorem essentially saves you, and you can make some sort of probabilistic estimates. Because what we're going to do is we're going to average over the contingencies, over the things that are special about each individual event, and we're going to try to get beyond what human agency can do. Because if I tell you my prediction is that you will vote like X or that you will do Y, then you can always simply choose not to do it. Given that you know that I predicted you're going to do it, humans we tend to be sort of contrarian. And so oftentimes, if I know that you predicted I will do something, then I will simply not do it just to follow your prediction. So individual agency ends up being a huge problem when you try to make predictions about events and violent conflict. If I put out a model that says there will be a terrorist attack on this street corner at this time, the terrorists will know the cops will be there waiting for them, and so they simply won't go. So the key here is to use these aggregate statistics to find these fundamental constraints, these things that tell you where are the patterns in the data, that tell you what kind of constraints all the individuals are operating under. These are limits to human agency, and this is where you can make predictions. Okay, so what are some of these patterns that allow us to make these aggregate level predictions? I'm going to go through three of these things. The first is a general pattern in terrorism. So this is a pattern over global terrorism. Let's just look at the number of incidents we have. This is a data set coming from MIT RAND database, which spans about 40 years at a time. There are about 40,000 events in this, and we're going to look at just the deadly ones. So they have to kill at least one person. These events are anywhere in the world over this 40-year period. So I just made a simple histogram. I've sort of binned things by order of magnitude, the first 10, the next 10, and so the next up to 100, up to 1,000, and then 1,000 and above. You all know what's going to go in this bucket right here. So what does the histogram look like? It looks like this. You can see pretty clearly that most terrorist events don't kill many people. In fact, the average is around 4 or 4.5. But these events over here are the ones that kill 10 or more people. You can argue that those are severe. But there's almost none of them. 8% of events. That's 8% of deadly events. And the deadly events are only about 14,000 out of 40,000. So the typical terrorist attack doesn't kill anybody. But we really care about these kinds of events out here. This is 9/11, of course, because that had a huge impact on reorganizing not just our national infrastructure in terms of counterterrorism, but also the entire world. The war on terror was produced essentially by that event. So can we build a model on those severe events in order to make some predictions? Okay? We're not going to drill down to the individual sort of characteristics of these events. Instead, we're going to try to get some sense of the population. If you take the logarithm of the y-axis, then you see that there is one of these patterns that emerges out of this data set. You can see that you have this very nice, smooth fall off. There's 9/11 again. And if you fit a model to this, you see that, okay, it is consistent with a very, very simple model that tells you what is the relative frequency of these different events at different sizes. This is a power law type model. Power laws get talked about in a lot of contexts, especially in complex social systems, and terrorism and violent conflict certainly qualify as a complex social system. So what we can say is that we can describe these data using this very simple model, which gives us a way of making probabilistic estimates about the likelihood of an event. We'll see this come back a little bit later. We'll actually use it to make an estimate of how likely 9/11 was to happen in the 40 years, given the historical data. So if we knew about all of this data to begin with, and we didn't know that 9/11 was going to happen, could we have made a probabilistic estimate of the likelihood that it was going to happen? Okay. So this power law pattern turns out to be very robust. If you look at other covariates associated with these events, you find that this power law pattern occurs in different decades. If you look at the events in the 70s, or the 80s, or the 90s, et cetera, this power law appears in all of those events. It also appears over different weapon types. If you look at just the events that use guns, just the events that use fire or bombs, all of them have power laws in their tails. It also holds for countries with different levels of economic development. So if I cut the data by events that happen in the OECD versus events that happen outside the OECD, I see power laws there too. But what's interesting is that there's not a universal power law. It's not one model to rule them all. Instead, the exponent alpha, this one parameter that tells you the slope of this power law, it varies across these contexts. The shape varies, and that makes prediction harder because the details end up mattering. There are even places where this power law doesn't appear at all. So for instance, if we just look at suicide attacks alone, we find that there is not any evidence that there's a power law in that distribution. If we also cut the data by looking at arbitrary regions, say North America or Asia, we also find that the power law fails there. And the reason is that contingency matters. The specific details of what's going on in Asia, which conflicts are ongoing at certain times, those things drive whether or not this power law appears. It's only when you pool all this data together that you start to see this pattern emerge, because then contingency sort of washes out. Okay. So one thing we might think of is try to drill down a little bit. We know that terrorist attacks are not done only by lone wolves. They're often done by terrorist groups. Terrorist groups have huge portfolios of events that they've carried out over their time. If you think about Hamas and Fatah, for instance, or Al-Qaeda, these things have long histories of carrying out events. So what if we look at the data sort of bucketed by the groups themselves? Is there any way of making predictions about what one group will do, or is too much contingency going to appear and spoil the prediction? So what we're going to do is we're going to take the 800 plus known terrorist groups in this data set worldwide over 40 years. We're going to ask just two very simple questions. One is, do older, more experienced groups create larger events? If that's true, if there's a correlation there, then we know where the large events are going to come from. We need to watch these larger groups. And then how often do they launch attacks? Are there patterns in the frequency with which these groups carry out their events? So because we have 800 known terrorist groups, that allows us to sort of average over the different contingencies that each of these groups is operating under. Each of them has their own agenda, their own constraints. By pooling all 800, we get a sense of what are sort of the boundaries of this parameter space. All right, so let's start with thinking about the severity of these events again. So we're going to take each group, we're just going to line up the events that they've claimed. That's an important caveat. So the first event they claim, the second event, the third event, and so on. We're looking at the severity of those events. How many people did each of those events kill? And the hypothesis is that, well, older groups have more experience, right? They know how to build bombs better, they know how to target better, they have more resources, et cetera. So you might expect to see that there's some sort of correlation between severity and experience. The more events you carried out, the better you get at killing people. So this is quite easy to do. Now that we've arranged things by the event number and how many dead there are, we can simply average over all the different groups. So this is the plot that we're going to create. So the y-axis is going to be severity of the next fatal event X, and then we're going to just look at the cumulative number of events that you've done. Now, it's important to note that most groups end right here. The average number, the median number of events a terrorist group carries out that they claim is 1. Most groups never get to 2. The groups that get out here to 50 or 100, these are the ones that you've all heard of, okay? So if we take all 800 groups and we ask, as experience increases, do we observe that there's an increase in the fatality? And the answer is no. Experience doesn't matter. The more events you've carried out as a terrorist organization, it doesn't help you kill more people, not on average, not across different groups. Why? Well, it's because that power law is hiding in the marginals again. So if you look at the distribution of severity here, and here, and here, and here, and here, what you find is that every single one of those marginals has a power law-like shape. This suggests that there's independence here. Whatever is driving the power law pattern in the severity of events, it's true for each event individually, independent of the experience of the group. We don't have a mechanistic explanation for why this power law exists, but that doesn't mean we can't use it to make forecasts. I'll make that in a minute. Now what about the timing of these events? Is it true that there's no correlation between how experienced a group is and when they carry out events? So we're going to do the same sort of thing we did before, but now we're going to look at the number of days between each subsequent event. So we take the first event and ask how many days does the group wait before they carry out the second event? How many days to the third event, and so on. So just as a cartoon, if they get slower with age, perhaps they ossify the same way that other organizations do. People get sort of happy with where they are. The organization gets big. You have lots of hierarchies. You have lots of other activities you're doing. So maybe you slow down with age. It's the young sort of startup terrorist groups, the ones that can move fast. Then you might expect to see this kind of pattern in which the delay is increasing as a function of the experience. So same sort of thing. We're going to tabulate the events as a function of the cumulative number of events here. Most groups are going to be down here, just as we saw before. We're looking at the time to the next event in terms of the number of days, so the delta t. What we find here is that they actually accelerate. So as the groups get older, they carry out events faster. This sounds like an experience kind of thing. In fact, if you have paid attention to the management science literature at all, you may have heard of these things called experience curves. They were first identified looking at industrial production in World War II for building planes. There are charts that look very much like this, which is how many days until Boeing builds the next airplane in the World War II effort. And they look exactly like this. The number of days is shrinking over time. So it sounds like the same kind of experience learning curve also holds for terrorist organizations, that they're getting better at producing this this good that they produce, which is death. Okay? So if you look at the marginals of this, you find this very nice data collapse in which every marginal looks like a log normal distribution. This suggests that we've really pinned down exactly what this model looks like, although we can't explain necessarily what drives the variance for any particular k. Okay? So this is still something we can use to make predictions. If I know that a terrorist group has carried out 10 events, then it gives me a pretty good idea about how long to wait before I see their 11th event. Because I just look at the marginal for 10, and that gives me my window of prediction. Okay? So let's try to explain why we see this particular pattern. Where does the experience come from? I'm going to argue that it's not actually experience or learning at all. It's just manpower. So if we have an organization with some size, they carry out some new event, the delta t between the previous event and the next one is going to be something like the inverse of the size. The size of the event is independent of that, as I've argued. And then that new event is used for recruitment. So recruitment, of course, leads to having a bigger size. You get more people coming in, you have more people who can carry out events. So that leads to having a larger group, which leads to a feedback loop. So the idea is that growth is what drives this apparent learning. Instead, it's just manpower. That if the number of people required to carry out a terrorist event is sort of fixed, then if I can recruit new people by carrying out events, then I have more people to carry out more events in the future. And the reason the timing between the events is going down is because the groups, these cells that I'm building, are working independently. If each of them takes 100 days to produce an event, if I have 2 cells, then on average it takes 50 days. If I have 3 cells, on average 33 days. So growth leads to this sort of natural shrinking of the time between events. So it creates this prediction that I should see this 1 over s behavior in the timing between subsequent events. I can simulate this process and just plot that variable. I can plot how long does it take between subsequent events as a function of how many events have carried out. And you see a pattern that looks exactly like what we see in the empirical data. The exponent is off by a little bit. This predicts a simple exponent of -1, whereas in the previous figure, the exponent was estimated at like 1.1. So it's very close, but it doesn't capture all of the variance here. But at least gives you a sense that just using the empirical data alone in order to make predictions about how long to wait before the next event is going to get you pretty close to what's actually going to happen. That really it's about manpower here. Okay. So the argument here is that attack production is really a labor-constrained variable. Bigger groups lead to more and faster attacks through this thing that I call this attack recruitment cycle. The acceleration rate, how fast it sort of moves down this curve, how fast they can recruit, does vary by group ideology. What we find in other analysis I'm not going to show you is that religious groups progress more quickly. So they grow faster, and that allows them to carry out attacks more quickly than, say, secular groups. Okay? But the attack severity is independent of labor and experience. So even though you have more people, maybe more supply lines and so on, able to create these events, that doesn't actually allow you to kill more people in each individual group. But combining these things lets you get a sense of how to make predictions about what will happen in the future, which is the older groups are more deadly. They kill more people in aggregate because they try more often. It's not that they're more successful with each individual event. It's just that they're carrying out so many more events that on average they're killing more people. But this also means that if I condition on there being a large event, the probability that it comes from a large group or a small group in that moment is the same, right? The severity is independent of how old I am. That implies that the largest event that we've ever seen could come from a group we've never heard from. So if you want to mitigate the risk of large events, then focusing on the older, larger groups is a good strategy because you know that they're carrying out a lot of them. But it's not going to allow you to eliminate the risk completely because these small groups that you're not looking out for have just as much of a likelihood of producing a big event as the big ones do. Okay. So this says that if we want to reduce the risk of large events, we should starve the beast of recruits. We should keep these large groups from growing as much. That leads to less growth. That leads to fewer events. That leads to lower risk overall. Not zero risk, just lower risk. Okay. Okay. So those are 3 sort of stylized facts that we've pulled out of the data by looking at these very simple models, looking at what are these fundamental constraints that shape the severity and frequency of events. We found one strong constraint, this hypothesis that is a labor constraint on the size of the group, and that drives the production of events overall. But we don't have a sense of what the constraints are for the sizes of the events themselves. That seems to be unconstrained in terms of the group characteristics in particular. So can we take these things and try to make some sort of prediction overall about the likelihood of a terrorist attack? So I'm going to claim that yes, you can. to some degree. So let's walk through this. Instead of predicting, I'm going to call it forecasting, because I'm not going to say who, what, where, when, why, or how. Instead, I'm going to make some sort of probabilistic estimate. I'm going to use 9/11 as an example here because it's the largest event, so it's fairly easy to think about. All right, so to do this, we're going to need a probability model. We need some probability of the size of event x. We know this is going to be a power law because I've shown you those patterns already. So the key observations here are that to make this kind of a forecast, we don't really care about the small events. Right? The large events are the ones that have this disproportionate consequence, and so we really only care about them. The second observation is we really don't know exactly what the upper tail structure is. What is the right distribution for the size of the events? I argue that a power law fits the data well, and it does, but without a mechanistic explanation of why that power law appears, we can't say that that's the right model. So because we don't know the exact upper tail structure, we really should be using several different models. And statistically speaking, several models do fit the tail in an acceptable kind of way. And then finally, the problem that makes all of this rare event prediction hard is there's just not a lot of data up there. Right? That's going to naturally produce large statistical uncertainties. If I fit a model to 37 data points, who knows what those parameters really should be like, right? For this kind of sense, we have these very heavy tail distributions, high variance. We're not going to be able to pin down those parameters exactly, so we're going to have large statistical uncertainty. So these three observations constrain the kinds of models that we can build if we're trying to make predictions. The solutions here that I'm going to describe are the following. We're going to first separate the tail from the body. That allows us to focus on the large events. So we're going to ignore events that only kill 1 or 2 or 3 people. And we're going to focus on events that kill 10 or 100 or 1,000 people. We're also going to use multiple tail models. As I said, because several models fit well, we should just consider each of them as being a plausible explanation for what might happen in the future. That multiple tail model will allow us to sort of control the model uncertainty. This is a very different kind of uncertainty than statistical uncertainty. If I choose one model and I fit it to my data, then I can get some estimate of how tightly estimated those parameters are. That's statistical uncertainty. But if I choose the wrong model, then I'm hosed. Right? So instead, I'm going to allow multiple models, each of which might have different kinds of assumptions built into them. That allows me to control the model uncertainty. As a scientist, it's a little bit hard to really embrace this second point really strongly because we really like to be right about our models. We want to say, this is how the world works right here. But if you're interested in prediction or forecasting, often you don't know what the right model is, especially for complex social systems. So instead, thinking about having multiple models, each of which fits well, that's a sort of a safer assumption, a more conservative approach in order to control the true amount of uncertainty you have, because you actually don't know what is the right model or the right parameters. Okay, so separate the body from the tail, use multiple tail models, and then we're going to use a distribution over conclusions. So that's going to be the way we account for statistical uncertainty. So this allows us to produce these model-based data-driven forecasts that integrate over multiple models and allow for statistical uncertainty. All right, so you've seen this picture before. This is the distribution of severity. Here's 9/11 again. This is the event that we're going to try to forecast. What was the likelihood of seeing this event historically? We're going to use 3 different models. I showed you the power law model before. There are 2 other kinds of heavy tail distributions that fit this data pretty well. One is what's called a stretched exponential distribution. This is a Weibull distribution if you're familiar with the lingo, as well as a log normal model. So all 3 of these produce statistically plausible fits to the data. They look like this. You can see now that the 3 models, which are colored red, green, and blue, correspond to sort of a range of pessimistic versus optimistic. The power law has the largest variance among all 3 models, and you can see that it places the most probability on the 9/11 event relative to the green and the blue lines. That's because it has the higher variance. The log normal model you can think of as being like an optimistic estimate of the shape of this distribution because it places less density on the event of 9/11. But nevertheless, they do all capture the variability of these not largest, but still fairly large events. So this is a way we're going to capture the uncertainty here in terms of modeling. They're going to produce different estimates because they have different statements about how the curvature of the tail behaves, whether or not it's higher or lower. So given these 3 models, we can use Monte Carlo to estimate the posterior distribution of the fraction of simulated histories that have at least one 9/11 sized event in them. So that's just a fancy way of saying we're going to simulate the heck out of this thing in order to sample from this complicated distribution, and that's going to give us these posterior estimates of the likelihood of seeing at least one 9/11 sized event or larger. Okay. If we do that, these are those distributions. So this is the probability of seeing at least one I'm calling it catastrophic event, in the 40-year period. And you might notice that none of these distributions are crunched down here at 0. There's some famous person who once said that if there's even a 1% chance of a large terrorist event happening, then we should do something significant. I think his name was Dick Cheney. So that 1% doctrine says that if any of the density is to the right of 1%, then we should be very concerned about it. And in fact, all the models agree that the likelihood of seeing an event the size of 9/11, not seeing 9/11, remember, we're not talking about what, where, when, why, and how. We're talking about just the aggregate, so just the size here. So the per event probability that the models produce, each of these things is tiny, 0.000, I think I got the right number, 003. For the second power law model, that's a tiny probability of a large event per terrorist attack. But there are 14,000 of them in the data set. So the product of 14,000 times this tiny probability, that gives you an expected number of about 0.34, 0.35. So it says that historically speaking, based on the high variance in the severity of terrorist attacks, we should have expected to see some event of roughly 3,000 people dying over this 40-year period, just given the frequency of the events and how broad that distribution is of the severity. The fact that that power law distribution or that heavy tail distribution is such a robust statistical pattern tells us that we should expect to see these large events. All the models agree, essentially. Even the optimistic model, the log normal, says that the probability of seeing a 9/11 sized event or larger is about 11%. That's not 0, it's not 100, it's just an uncomfortably large fraction, considering we're talking about 3,000 people dying. That was the 40-year probability. Now, if you have a notion of how often you're sampling from this distribution, say I have 100 events this year, 200 events the next year, and so on. If you have some notion of how to forecast the number of draws from this, you can also use this kind of model, which is a historical model, to make an estimate about what the future will be like. That then depends on knowing, is terrorism getting more frequent or less frequent? In the paper we wrote on this, we did make such a prediction, but the paper was written in 2013, so it's a bit dated now, and our forecast window was 10 years, which ends in 2 years, ends in 2021. I won't tell you what we said was going to happen in those 10 years because, well, I don't want to spoil the surprise. Okay. So here's a recipe for large event forecasts in political conflict. So the first suggestion is only focus on the large events, meaning separate the body from the tail, because we really don't care about the small events. Right? If a war only kills 100 people, it's probably not that big a war. If a war kills 100,000 people, probably we care a lot about it. So separate the body from the tail and then use these tail models, then use multiple models in order to capture the fact that we don't really know what the mechanism is that produces these events, so therefore we need to control for our uncertainty about the models. Third, compute distributions over outcomes. Because there's not that much data in the tail, we're going to have a large statistical uncertainty, we need to control for that. So these distributions here give you some sense of how certain are you that something is going to happen or not. And then finally, you can take these kinds of event-based models and combine them with notions of time series, so how often are we sampling from the distribution, in order to get some sense of what's going to happen in the future. If there are more events happening per unit time, that necessarily implies that there's greater risk. So this is the independence assumption that David mentioned, which we're saying that we're going to assume that each draw from the distribution is independent. We know that that's not exactly true. Right? We know that events are correlated. But because we're pooling data together across the entire world, the events that happen in Colombia are relatively independent from the events that happen in Sri Lanka. And as a result, we can treat them as being effectively independent. Now, if there's something were to happen to sort of tie together those probabilities, to correlate them to some degree, then this model would end up not capturing that, and as a result would be potentially wrong. But for the most part, the political events that drive terrorism tend to be local. So this is a relatively good model for making predictions at the global scale. If you wanted to take these kinds of models and make them specific to an individual conflict, say you cared about the Colombian conflict, or you cared about the conflict in Iraq, then you're going to run into a problem. Because this model includes no information about the particular contingencies that shape the frequency and severity of events in that one conflict. It may be true that there are patterns in those conflicts, but they're not going to necessarily be represented in this kind of model, because this model is being as simple as you can be in order to make relatively robust forecasts or predictions. As you sort of drill down into those details, contingency is going to be more and more important. But what's problematic is that we don't know for certain at what scale in terms of time or space contingency ends up being important. So can I go from a global model like this down to a theater level model? Maybe. Can I go from a theater level model down to a group level model? Maybe. Can I go from a group level model down to an individual cell model? Probably not. It's somewhere in that spectrum, contingency, historical or present, is going to spoil the effects of the averaging that we're doing here. And as a result, the details that are important for that one person pressing that trigger or designing that bomb, those details will be important. And as I claimed at the beginning of the talk, I don't think it's possible to use algorithms to make predictions about that level of granularity. There's just not enough data. Plus, you have the problem of human agency. So this is my recipe for making these large event forecasts. Start with the population, all terrorism or all wars, and aggregate. You can add the covariates to the model, but you really need to avoid overfitting, which is always easier said than done. And it's, I think, better to have greater uncertainty than to have false certainty. Right? It's better to say, I have a broad distribution, I'm not sure what's going on, than it is to say, this is exactly what's going to happen, and then be spectacularly wrong. Okay. So let's step back a moment and think about this general sort of agenda of prediction in violent political conflict. And before we talk about that, let's talk about seismology, because seismology has a long, long tradition of actually making predictions, making forecasts. In seismology, we know what the physics are that generate earthquakes. Earthquakes are not out to get us, which is helpful. There's no agency there. And we see the same kind of power law-like statistics. The Gutenberg-Richter law is one of the most well-known and oldest examples of power laws in complex systems. And it says the same thing we've seen with conflict, which is that the frequency is inversely proportional to the magnitude. Right? The bigger events happen less often, that's kind of obvious, but they happen less often in a very, very regular way. And in California, they actually built regulations about how you build houses and buildings around this kind of statistical pattern. Even though we don't know exactly when the next big one is going to happen in California, we nevertheless know how often to expect moderate-sized earthquakes. You could do the same thing with terrorist attacks and wars because the statistics for those are so stable. In fact, they look just the same, right? International wars also follow these power law-like statistics. The largest events are the ones you know, World War I, World War II, and a few others. And these things have the same statistical structure as terrorist attacks. It's intriguing that in political conflict, this kind of a pattern appears so robustly. It suggests that there's something interesting going on, perhaps, that drives these things, but it also says that prediction is going to be very, very difficult. If the probability of drawing a large war follows this power law-like distribution, which the evidence suggests that it does, then if I start a new war next year, the chances that it blows up to be a global conflict are not very small. As I mentioned at the very beginning of the talk, there have been 7 wars in the past 100 years that killed 100,000 people. So a 7% chance of a random war killing 100,000 people, that's not very small. So here's a nice little comparison, side by side. Earthquakes, Gutenberg-Richter law. Physics is largely known. We know what generates earthquakes. The processes are fixed, which is very handy. Forecasting is possible. We have years of success. We build laws around how successful our forecasts are about earthquakes. But it turns out prediction, who, what, where, when, why, how, that's very, very hard. And that's why people talk about the fact that San Francisco is, sitting on a fault line. We don't know when it's going to happen. Why are so many people moving there? You got me. I have no idea. It's not because it's safe. And in fact, we have years of failures about these things. At one point, the Chinese government decided that the people of China could predict earthquakes. And then there were a couple of really spectacularly bad predictions, and they took it back. The reason that prediction is hard is that we don't have the right data. We can't get the sensors in the ground in the right places to know exactly what's producing the coming earthquakes. If we could do that, maybe we could do better. But the history of looking at predictions in earthquakes is terrible. Basically, we're wrong all the time. Every hypothesis we have about how to predict next Tuesday at this time, this size, those things always end up wrong. So this is a process, this is sort of easy mode for making predictions using heavy tail statistics. And we're going to try to do it on hard mode with terrorism and war. at least we see that there's the same sort of empirical pattern, right? But the processes that produce this pattern are largely unknown. We don't know why there's a power law in the sizes of wars. We don't know why there's a power law in the sizes of terrorist events. And what's worse is the processes are dynamic and adaptive. Human agency means that if I tell the world why it is that terrorist attacks have this distribution, people could just change the mechanism because they're contrarian. So a dynamic and adaptive means that we're sort of trying to build models on sand. Forecasting is possible over the long term, it seems like, because these patterns so far have been so robust, that these patterns do exist in the data. But prediction is really, really hard because of agency and contingency. So is there hope of doing this, prediction for these violent conflict events, when there's already failures on easy mode? It's not clear. I, for one, am sort of pessimistic that prediction is going to be possible here, even with massive amounts of data. I think that's likely to lead us to be over-optimistic about how accurate our predictions are. Instead, I think forecasting is probably the best we can do. So to come back to the beginning, large events in political conflict, can such events be predicted with algorithms? No. Well, it depends, really, on what kinds of predictions you're trying to make. Recall, if you try to make specific predictions, who, what, where, why, how, and when, I think the answer is no, because there's not enough data. The space of parameters is too high dimensional. There are too many relevant variables. There's too much historical contingency. History doesn't repeat itself exactly, and as a result, you're going to overfit to things that aren't going to help you predict the future. But if you do it in aggregate, then I think you can make these statistical forecasts. You can make these risk estimates, because these robust patterns, some of them do exist in the data, and they allow probabilistic estimates over entire populations, not individuals. So that allows us to average over these contingencies, to get beyond individual agency, to focus on these fundamental constraints. The idea, for instance, that labor, availability of manpower is what drives the frequency of terrorist events. It suggests also that the best predictions we can make are going to be made using multiple means, so different models, controlling for model uncertainty, and then also controlling for statistical uncertainty. That's sort of the only way that we can get reliable, trustworthy predictions about what might happen in the future in these contexts, in terms of probabilistic estimates. Okay, so I want to thank a lot of people who have helped with this work. Co-authors are on the top. Friends are in the middle. There's a bunch of papers here that I've written about sort of forecasting and prediction in this context with violent political conflict. This one right here is not about conflict in particular, but it's actually about power laws. And it argues that it shows evidence for power laws being sort of ubiquitous phenomenon across complex social systems. So if the context that you want to make predictions in is social, and it is complicated, then you should look to see if you have these heavy-tailed distributions in your variables. And if you do, then everything I've said today is probably going to be relevant. You're not going to know exactly what the mechanism is that produces it, so you should use multiple models. There's going to be not a lot of data out there in the tail, because unlike in physics, we don't have Avogadro's numbers of people, 10 to the 23. Instead, we have like hundreds or thousands, maybe hundreds of thousands sometimes. But those are small numbers when you're talking about events that have tiny, tiny, tiny probabilities. For instance, we would like to know what the probability is of a nuclear terrorist attack, but there haven't been any. So how do we build a model on something that we have no data for? Ugh. If you have these power law distributions that occur in your system, it's going to be really hard to make good predictions because of that variance. So with that, I'll leave you with a teaser. The first paper, Trends and Fluctuations in Severity of Wars, looks like this. Thanks.
Thank you, Aaron. Are there any questions for clarification?
I see I left lots of time for questions.
Yeah.
Please. If you'd like, I can explain this figure.
Well, why don't you do that?
Okay, great.
Since that's a teaser.
So the question of this paper was about the long piece. So war is a terrible, terrible thing that we humans do to each other. We've been doing it for a long, long time. In this case, this data set goes back to 1823. This is the correlative war data set. There are only 97 international wars in this data set, which is most of the international wars that have happened in this almost 200-year period. So there's not a lot of data. And the severity of wars, as I argued, also follows a power law distribution. So the size of the largest ones, like World War I and World War II, are truly stupendous in size. And the world was smaller back then, too. If we had another event that had the same sort of parameters of World War II, it would kill a lot more than 17 million people in battle. That was the battle death size of World War II. So in this paper, I wanted to ask the question of, is the long piece, as it's called, which is the idea that, well, we haven't had any really stupendously large wars since the end of World War II. Maybe the rules have changed. Maybe somehow we've become more peaceful or better at navigating our disagreements politically between countries without using guns or tanks. And this is a popular hypothesis. Lots of people believe it's true, and there's lots of evidence to suggest that we have gotten better at not going to war with each other. But the larger question is whether or not that's going to stick, whether or not we should expect the long peace to happen, to unfold for many, many more years, or whether it's sort of a fluctuation. And a fact about these power law distributions is because the variance is so big, I can draw values from this distribution many, many, many times and never see a big one. And that's just an accident. Even though the distribution is fixed, the chance of a big one is the same for every draw. The chance that I see that big one is very small, and as a result, I'll go through a long run of small things without knowing that there's a big thing coming down the line. So the question about the long piece is that. Is the long piece just a lucky set of draws, or is it somehow reflective that the rules have changed? So we can use statistics in order to answer that question by building what's called a stationary model on the past. To say, let's imagine that the past is one of these stationary processes in which everything has the same fixed probability, and we're just drawing independently from that distribution. And then we can ask, well, how long can we go before we see something that's the size of World War II or some other large event? So in this case, what I've done is I've taken the data and stratified it into quartiles. So the blue line is everything, the red line is the top 3 quartiles, the green line is the median, and then the black line corresponds to the top 25% of events by size. So the big events, the ones that kill 100,000 people, are all down here. Things like the Iran-Iraq War, the Korean War, and so on. These are down here. You can see this period right here. This is what I call the great violence in the paper. This is between World War I and World War II inclusive. This is when humans were really good at killing each other, and we did it a lot. And this is the long piece right here. Very few of these large events. And the question is, if I extrapolate this trend out into the future, at what point does it start looking unusual relative to the historical pattern of just drawing these events IID from that distribution? And you can see each of these gray lines is a simulated trajectory. I'm going to simulate many, many, many histories. I'm going to look into the future, so I'm going to draw more events down the line. I'm just going to ask, at what point does this dashed line exit the envelope of probability for these large events? And the answer is about 100 years. That we can't tell if all the amazing things that we have done to ensure peace in the world have actually changed the underlying rules that produce events, because the events are so rare. 100 more years of waiting before we know if economic integration, globalization, spread of democracy, et cetera, if those things have actually changed the rules of producing war sizes, that's a long time to wait. But it's that long because these events are so rare. 97 wars over 200 years, that's one war about every 2 years. That's how often you get to draw from that distribution. It's not very often. It's a lot slower than with terrorism. So the punchline was, we can't tell yet if we've really changed the world. We should keep doing what we're doing maybe, and then wait another 100 years. Okay, I'll end there, thanks.
Thank you. Any other questions?
Going back to the terrorism attack question.
Yeah.
How much are you concerned about the endogeneity inclusion on both the low end and high end, in the sense that tons of terrorist organizations commit 0 terrorist attacks, and how much are you thinking about how that impacts the way you're thinking about this? And then, of course, a terrorist organization could graduate, I guess, into a military organization and use the data set on the high end if it becomes a recognized armed conflict. How should we think about that affecting a lot of your results?
Yeah, so it's a great question. Just to clarify, as I mentioned before, most groups start and end here. Actually, most groups, if you imagine the ones that aren't even in the data set at all, start and end at 0. These are groups that think they're going to do something and they don't kill anybody in the end. So as I move along this axis, I'm downsampling my groups. I have fewer and fewer groups. The ones that end up here, these are the ones that look like militaries, like Hamas, for instance, which has a political wing, a military wing, it has wings for social services and so on. So when you get out here and you can carry out an event every day of the year, then probably the rules change, right? You're no longer a startup company, now you're an entrenched corporation. And you probably act like a corporation in many ways too. So the idea is that this pattern that we see is really about how groups emerge and get established. Once you're established, then I think the rules are certainly going to be different.
Yeah. Clarification on your last. Oh, yes.
I'll try to repeat the question too.
Clarification on your last chart about predicting the wars.
Yeah.
One of the theories behind the long peace is not so much that we've gotten better at managing these things, but the presence of nuclear weapons has created a deterrent factor. And is there enough data to separate wars between two nuclear powers versus other powers that gives you different patterns that suggest nuclear weapons do have some kind of effect?
The question was whether or not nuclear weapons are a part of explaining the long peace. And I would argue that scholars of peace think that there has been some effect. But the thing is that it's confounded by a bunch of other factors. So nuclear-armed nations also tend to be economically well-developed. Those nations also typically don't go to war with each other very often. They also tend to be democratic. Democracies tend not to go to war with each other very often. So is it the nukes or is it the democracy? Is it the nukes or is it the economy? It's not clear. So I think that without having enough data to say one way or the other, we can't. So we can theorize about it, and I think that those theories are plausible. But whether or not it's the right explanation, I think it's too early to say.
Yes, sir. One more.
I'll repeat the question.
What happens if all of these models based on the rating number of casualties, deaths, organization size, capability. So there's a hypothesis which is that essentially somebody who kills 9 people is not going to be, it's not going, an organization that averages 9 or 10 deaths per incident is not going to be the one that is going to give us the big disaster.
So the question was about whether or not organizations that typically kill a small number of people are likely to be the ones that also produce an event that kills hundreds or thousands. Is that right? So the evidence suggests that there is no correlation there, that an organization that ultimately goes on to kill 1,000 people in a terrorist event will have carried out many small events prior to that. And so prior to that large event, they will look like an organization that doesn't kill many people.
Okay, but what happens if you introduce technological change so that an organization that's only capable of, let's say, killing 9 or 10, all of a sudden has full capability. Now a million. Well, a million.
So the question was whether or not access to certain technologies might help us make better estimates about whether or not an organization could go from killing a few people to killing a lot of people. And I think that 9/11 is a great example of low technology killing a lot of people. With terrorist attacks, in the data set, the vast majority are actually bombs. And bombs are relatively easy to make these days. And if you place the bomb in the right place, you can kill a lot of people. And so the idea that, at least for the events that we've seen, that kill up to about 3,000 people, that there is a strong technological component there doesn't seem like it's well supported by the evidence. Now, if you wanted to ask about nuclear terrorism or biological terrorism, then there's clearly a technological component there. But we have no data to suggest how likely it is that an organization is going to acquire that and then use it. And this gets back to the question of whether or not we can use data to make predictions here. And I would argue that in that context, because we have no data to go on in the first place, and the processes there are so specific and contingent, that's a place where we should not rely on algorithms at all. And instead, we should rely on human expertise and evidence trails. Great.
Gregory, thank you very much.
Thank you.
We'll now take a 15-minute break and reconvene at 10:15. Thank you.